So now we start the chapter 3 in the series of theory of machine, the chapter 3 being the flywheel. The topics that we will be covering in the flywheel will be: first we will cover the turning moment diagram, and second we will cover the sizing of the flywheel. So these are two subsections. Now first we will define what is a flywheel. So a flywheel you might have seen in many engines. In IC engines, there is a cylinder block, then there is a crankshaft, and power is transmitted. At the outlet of exit of the engine, you must have seen a big wheel of solid mass, which is not having any function related to the transmission of the forces or the working of the engine, but it is just attached to a shaft, and then this is coupled to the output, whatever it may be a generator or it may be vehicle. So this intermediate thing is a flywheel, which is a solid mass of metal or something, and it is just connected to the engine shaft. What is the purpose? Heavy mass that is connected to the engine. So this is a device which is used to absorb the energy when engine is producing excess energy, and it provides the excess energy when the power from the engine is less. So I write down a definition for flywheel here. The flywheel is a device which serves uh, as a reservoir of energy. So the reservoir will store energy when supply of energy is more than the requirement, and it will supply energy when the requirement is more than supply. So this comes in picture partly with respect to IC engines, normally not in gas turbine or another engine which are providing a constant thrust, because in IC engine we have a fluctuating thrust on the output shaft. Why this is because if you recall the IC engine cycle, so the pressure will be less, then during compression the pressure will rise, then during ignition it will rise again, then during exhaust it will fall down to come below atmospheric, the exhaust will take place, and then again the cycle will repeat. So this is the pressure axis and this is the crank angle theta. So the pressure in cylinder varies with the crank angle, because in IC engine power is produced during power stroke, and for the rest of the stroke the energy is supplied from the crankshaft. So the compression stroke requires energy from the crankshaft. So that is why the torque on the crankshaft is not constant. It keeps varying with the crank angle, that is time. Therefore, you have a fluctuation of input power. So during the power stroke, you get energy, and during the compression stroke, you supply the energy. So that's why you can see the definition of the flywheel. It acts as a reservoir to store the energy when supply of energy is more than requirement. So that is during the power stroke. Usually the torque is more than what is required at the output, and it will supply energy when the requirement is more than supply. That means during the compression stroke, when the engine itself requires a source of power and along with the load. So to keep this fluctuation within limits, a flywheel is used. So the first requirement for doing calculation of a flywheel is to the understand the fluctuation of energy. So for that we have to look into the working of a IC engine or a reciprocating engine. So we will consider the torque in the reciprocating engines. So we have two type of reciprocating engines basically in industry. One is the internal combustion engine, IC engine, where the combustion takes place inside the cylinder. The second is the steam engine, where intermittent, like with time it will vary. So intermittent supply of steam will be there. So both of this will have the different strokes. There is one power stroke when in IC engine combustion takes place and expansion of gases takes place, and in steam engine in the power stroke the steam expands to create thrust on the piston and drive the crankshaft, and then you have a compression stroke. In the compression stroke, the in the IC engine the gases are compressed. So during the power stroke, power is produced, while in the compression, gases are compressed in IC engine. For the steam engine, is somewhat different. That I'll just illustrate so shortly. And then we have the third stroke, which is the exhaust stroke and the intake stroke. So during the exhaust stroke, work has to be done on gases to expel them out of cylinder. And so in the case of steam turbine, this is an important component because the steam will expand, and after expansion, the steam will have sufficient volume, and you have to do significant work to expel them out of the cylinder. And then you have an intake stroke, and in the intake stroke, you have to pull the gases in the cylinder. So that also you have to do work. The pressure in the cylinder will fall, so there will be negative pressure on the piston, and the piston will be pulled upward. So this is predominant in IC engines, where you have to pull the air in the cylinder, and for that you have to take power from the crankshaft. So as you can see here, the requirement for the IC engine and steam is a little bit different. And the intake stroke for the steam engine, you don't need to supply that much power because steam by its pressure will inside, will come inside the cylinder. So you don't have to give that much power during the intake stroke, but during the exhaust stroke, you have to do work on the gases to push them out of the cylinder. That is important for the steam engines. And the compression stroke is predominant in IC engines. So the stroke to stroke power consumption or power supply, power consumption or supply depend very much on design and operating cycle of the engine. So this is too much of the information that we can consider in the subject of flywheels. So this information, stroke to stroke power consumption or supply, this will be a given information for us. Given information for design of flywheels. So actual derivation of this stroke to stroke power variation will be covered in a separate chapter itself. That is the theory of IC engines or the theory of steam engines. And we will hear consider that this information is given to us, and with that we will go on designing the flywheel. So given that the turning moment diagram of the engine would be given. So what is a turning moment diagram? Definition of turning moment diagram. It is also called a crank upper diagram, and it is a graphical representation of the turning moments for different position of the crank. So as far as flywheel design is concerned, we will be just worrying about the position of the crank. We will have a crankshaft. It will be having power supply from the engine. There can be multiple block engine. There can be single engine. So there will be some torque produced on the crankshaft. This is the crankshaft, and our flywheel will be attached to this crankshaft. This is the flywheel. So we'll just consider that the crankshaft, we have some angular displacement theta. So crank angle theta, and at that particular instant, at particular time instant t, the crank angle will have some value. Crank angle will be, let's say, theta. So that time instant, the torque will also have some value, let's say t. So we will be considering the graphical representation of variation of t with respect to theta. If we have this information, then we can go ahead with designing a flywheel that we will cover in the section 2 of this chapter. For understanding the turning moment of various engine, we will take up some typical cases. So first we will take up a case of a steam engine, a simple steam engine. So steam engine, if you see the cylinder and the piston, it will have a inlet valve and a exhaust valve. So when the piston is at PDC, and that time the inlet valve is open and it will allow the steam inside. The steam will push the piston downwards, so the piston will start moving towards the bottom dead center BDC, and after BDC it is again going up by inertia of the crankshaft to expel the exhaust gases out. So if you consider TBC as 0 degree crank and BDC as 180 degree crank, then if you draw the diagram of torque versus crank angle theta on a graph, then you will find that during the intake stroke, the torque is positive because from 0 degree to 180 degree, torque is positive because gases expand, push the piston down, and the piston supplies energy to the crankshaft. The piston drives the crankshaft. So if you see the diagram, the torque will not be maximum immediately. With the inlet, the steam will start coming in, they will expand, so the torque will rise with time, and then somewhere 90 degree or just before 90 degree, it will touch the peak. So this is 0 degree. To touch the peak, and then after 90 degree, when it's in the middle of the travel, the piston is at middle of its travel, it will start decreasing, and then when the piston reaches BBC, it is 180 degree, the torque will be 0 again. So the piston will just sit there at the BBC. Now it will start to go back top again. So by inertia of crankshaft, the piston moves from 180 degree to 360 degree. So the return motion takes place due to inertia of the crankshaft. This inertia of the crankshaft is precisely what is defined by the flywheel that we will define in the next section. How to calculate this inertia. But for now, we will just understand the nature of the torque diagram. So during the return stroke from 180 degree to 360 degree, the crank will be supplying power to the piston current connecting rod. So the torque will be negative. So this is positive, this is negative. Torque will be negative and it will go and reach the TDC again. 360 degrees TDC, 0 degree is also TDC, and at that moment it will again become 0. So this is what the simple steam engine cycle will look like. So in the exhaust, this is basically the stroke, exhaust or return stroke, where the power is supplied from the crankshaft to the piston. Power or torque is transmitted during the inlet and power stroke, which is combined inlet plus power stroke. The torque gradually rises, reaches a maximum around 90 degree. Torque is maximum near 90 degree, and then it starts declining and reaches 0 at 180 degree. This is a simple steam engine cycle. Now we will consider the case of a double acting steam engine. So in the case of a double acting steam engine, you will have a cylinder, you will have a piston, and then you will have on both sides one inlet and exhaust, and on the bottom side also you will have an inlet and an exhaust. So the piston will move from TDC to the BDC. In this case, when it is coming back from BDC, the valve on the other side of the piston, the bottom side open and give a thrust to move back. So if you draw the turning moment diagram for this case, you will see that from 0 degree to 180 degree it will be same. The torque will gradually rise during inlet and power stroke from side 1. Let's say this is side 1, this is side 2. So from side 1 it will rise, and then when it reaches the BDC, the torque due to the piston 1 will be 0. But when it starts moving again from BDC to TDC, that is 360 degree, this time piston 2 will supply power. So side 2 will supply power from crank angle 180 degree to 360 degree. So in the return stroke. So this time again the torque on the piston will be positive because the piston is driving crankshaft. So in this case there is no negative torque. The torque is positive always, and because in the return stroke for side one is power stroke for side 2. So that's why the torque is the will be determined, the negative or positive nature of torque will be determined whether the piston is driving the crankshaft or crankshaft is driving the piston. But so in this case, the piston is driving crankshaft always in a double acting steam engine. However, still there is a fluctuation of energy. Fluctuation of energy is there. So if you want to calculate a mean torque from the piston on the crankshaft, so you will take an average of all this torque, you will get a mean line. So this will be called a mean torque line. So if you see, some of the portion of the crank angle lies above the mean torque line, while some lies below the mean torque line. So the mean torque that is supplied from the piston to the crankshaft, excess energy is there sometimes, and sometimes there is a deficit of energy. So in this case also fluctuation of energy is present. In the earlier case, where for a portion of cycle the torque is negative, here there also you can draw a mean torque line. So there will be a portion of torque diagram which is above the mean torque line, and there's a portion which is below the mean torque line. So this fluctuation of energy about the mean torque line is of the main interest to us. So for flywheel, important thing is fluctuation about the mean. It doesn't matter whether you are in positive torque or the negative torque. If there is a fluctuation of torque on the crankshaft about the mean, if excess torque is there or deficit torque is there, there will be fluctuation of the angular speed of the crankshaft. We will try to calculate in the flywheel design. For understanding better the concept of fluctuation of energy, we will consider this diagram. It can be any general turning moment diagram, but we will consider for now whatever we have at present, that is for the double acting steam engine. The definition applies for all the turbine turning diagram. We will analyze this diagram in a little bit more detail. We will mark the various regions of this diagram. Let's say if you draw a perpendicular from here to the crank line, this point is A. Then if you draw a perpendicular from this line, from mean torque line, cutting the actual torque line, you draw a perpendicular on x-axis. Let's say this point is B. Similarly, for the other portion of from 180 degree to 360 degree, if you draw them cutting from the cutting point of mean torque line to the actual torque line, so this is actual torque line, these two both. Then let's say this point is C, this point is D, and then if you draw a parallel from the mean torque line cutting where the mean torque line cuts the torque axis, let's say this point is E, this will give you the mean value of the torque, and then you have F where it cuts with the actual torque line first, then you have a peak, let's say G, and then again the mean torque line cutting, then it is going down the bottommost point, let's say this is P, and then again cutting the second portion of the torque line, let's say this point is J, and this point, the peak, the second peak is K, the fourth point of cutting the torque line is L, and then the BDC, the TDC again 2 pi degree is, let's say, Q, and again here this point will be E. So as you can see here, the cycle repeats itself for 2 pi or 360 degree of crank rotation. So that's why we have considered a single cycle here. We will analyze for single cycle, and then that results will be applicable for the series of cycles, because all cycles are identical. This is assumption that we are making. There will be cycle to cycle variation in actual engine, but this thing we are not considering in the present design. We'll have a turning moment diagram that is supposed to be representative of all the cycles of the engine. So now you know that the area, the power is equal to torque into displacement by per unit time, that is angular velocity. So the work done is power multiplied by time, that is torque multiplied by omega into t. Omega into t is theta, the angular displacement. So work is equal to torque into theta, that is crank displacement. So what does this mean from the graphical representation? You have torque on y-axis and theta on x-axis. So the work can be derived by taking area under the torque and theta axis, because work is equal to is on the x-axis. So if you take any element on the torque theta graph, so the area of the element will be equal to the torque multiplied by theta. So T multiplied by theta is represented by area under the graph. For any, from your basic mathematics, you know this thing, that multiplication of both the axes is represented by area under the graph. So if you have any portion of the graph and you want to find out the work. Now, since work is equal to torque into theta, so hence the area under the graph represents work. So area under the graph, and it represents work. So hence you can find out energy from the T theta diagram. Energy from the T theta diagram by taking area under the graph. Now we will analyze this various portions of the cycle in the T theta graph, and what are the different kind of energies. Here you can see that energy is above the mean torque line. Here it is below the mean torque line. So what does this mean? This will be covered in the next video.